Hello everyone, welcome to this introductive video to single-case research design and effect size indexes. I am Isabella Giammusso from the University of Palermo. Together with Professor Alberto Mirisola and other professors and researchers from the university, we took part to the Behave project by creating the algorithm embedded into the Behave application for the analysis of data and results elaboration. I'm going to present to you the research design on which the Behave application relies on and on how to read the output of the application through an example.
This presentation is titled Single Case Design and Effect Size Index of a Treatment. And in the title itself, you can see some keywords that you will encounter often during this video. Thus, we are going to start with the definition of such terms. The single case design is the type research design on which the Behave application algorithm is grounded, and it is a particular type of research design. Instead of being based on the comparison between or within groups of participants, in this case we have only one participant, who is also his or her own control. This means that the outcome of interest is observed on one participant only, but many times during different phases. Then these measurements are compared. Let's take a look at the graph. It will help us to understand clearly how the single case design works. The points of the graph are observations of the same outcome of interest measured on the same person in different days. In this case, the outcome of interest is the severity of the panic problem. In this occasion, we are comparing two phases labeled as A and B phases. Generally, the A phase corresponds with the baseline phase, in which we observe the manifestation of the outcome of interest without intervening on it. Differently, the B phase generally corresponds to the treatment phase. In this phase, we introduce an intervention and we continue to observe and measure the outcome of interest. The comparison between the two phases will inform us about the efficacy of the treatment. This is the simplest form of single-case design, and it is known as A-B design. The A and B labels could also indicate phases like a baseline and a withdrawal phase, or treatment and withdrawal phase. The fundamental concept is that in this design you compare two phases. However, the mere observation of the graph is not enough to determine if our treatment is successful. It is important to have statistical indexes that provide to us reliable information about the strength and the direction of our treatment. The apparent decreasing trend of the behavior that you can see here could be due to the natural trend of the outcome of interest and not to the implementation of an intervention. Or you may have a graph in which the trend of the outcome is not clearly ascending or descending between phases. Thus, how do we know if the intervention is effective? In order to obtain this type of information, we included in the algorithm the computation of an effect size index. An effect size index is a number that synthesizes the strength of the treatment, and it is complemented with a sign, a minus or a plus, that represent the direction of the effect of the treatment. In this table, you can see two examples of effect size indexes. As you can see, here you find a number that informs you that the effect is null, small, medium, or large. The sign indicates a decrease when you see a minus, or an increase when you see a plus. The script of the Behave application is able to calculate the effect size of a treatment with two possible approaches, a parametric and a non-parametric one, and to suggest to you the one that better fits with your data. Both methods take into account elements like the effect of time on the outcome of interest, or the impact of the treatment on the level and the slope of the outcome of interest, as in the case of the parametric method elaborated by Ellison and Gorman. Here you can see all the elements it considers. Parametric statistics can be applied only when data satisfy certain criteria. When these criteria are not met, we can use non-parametric methods. Here you can find the non-parametric solution that we included into the algorithm of the Behave application. It is elaborated by Parker and colleagues, and it combines non-overlap with trend. The script that we elaborated computes both indexes, then provides to you the better solution for your data, so that you don't have to choose between the two possibilities, unless you want to. In fact, the results given by both methods are at your disposal if you are interested in them. In the Behave system, you have a wide selection of measures to observe the outcome of your interest. Here you find a couple of examples. You can choose to make scale to rate the degree of anxiety by using numbers only. In this example, 0 represents a low level of anxiety, and 4 represents a high level of anxiety. You can also decide to combine numbers with faces representing the corresponding degree of anxiety. You can also choose to use the visual analog scale. This is a very flexible measure and can be adapted to a wide range of outcomes to be observed. It is composed of a line anchored between 0 and 10, and the degree of stress or happiness, or whichever is the outcome of your interest, can be indicated on a point on the line. Depending on your particular case, you can choose and customize a measure and you collect data with it. Thus, what happened when you collected the data? Let's take a look to the output that the Behave application provides to you after the system has elaborated data and how to read the output. Once you collected data, you have to choose the phases to compare. In this example, we are comparing the baseline and the intervention phase because we want to understand if the treatment is effective. Thus, you select the phase to be compared, and the application elaborates information, analyzes data, and produces the output that you can see here. Look at the graph. You have 5 observations for each phase. This means that we used the same measure 5 times per phase to monitor the outcome of interest. In this case, the frequency of interruption during conversation. It is fundamental that you collect at least 4 observations per phase, otherwise the algorithm will not provide to you this output. On the right, you can see a speedometer. In the speedometer, you can distinguish different colors and you can see an arrow. The colors represent the strength of the effect of the treatment. The orange color is associated with a large effect. The yellow is associated with a medium effect. Lilac is associated with a small effect, and in light blue you find the null effect. Here you have the arrow that indicates where the effect size of your treatment is. Moreover, you have some numbers here that also represent how strong your effect is and the direction of the effect of your treatment. Remember, minus represents a decrease, while plus represents an increase. So, now let's try to combine all this information and read the outcome. The arrow points at an orange area, and this means that the effect of the treatment is large. But the arrow also indicates a point comprised between -1 and -0.5. So, this means that the treatment has a large effect on decreasing the outcome of interest. In the present example, this means that the treatment has a large effect on decreasing the frequency of the behavior of interruption of a conversation. To help you to read correctly the output, you can find here a clear statement that describes your results. And this is it. Thank you for having followed us with this brief presentation and for your attention.